mind-bending journey today.
Definitely mind-bending.
You sent us some fascinating sources asking about the Planck scale.
Yeah.
Specifically, whether there's an ultimate minimum frequency length. Basically, the smallest possible wavelength or distance in the universe.
A fundamental pixel size for reality, maybe.
Exactly. So our mission for this deep dive is to explore these sources and figure out if there truly is an ultimate operational limit. Like, how small can we actually measure in space-time?
And importantly, why?
Yes, why. We'll see why this limit isn't just some random number somebody picked, but actually a really profound consequence of the universe's own fundamental laws.
Yeah, what's truly fascinating here, I think, is how your question really probes the foundations of reality itself.
Yeah.
We're going to have to connect the biggest ideas in physics, quantum mechanics for the small stuff, and general relativity for the big stuff, for gravity.
Let's see how they clash.
Well, how they combine, actually, to reveal this surprising boundary to what we can empirically know. It's quite something.
Okay, let's unpack this then. Our journey to the smallest measurable distance begins not with, like, a tiny ruler, but with three fundamental cosmic constants.
Right. Think of them as the universe's basic ingredients, the pillars holding up reality.
Foundational pillars, I like that. They define how everything interacts.
Indeed. And first up is the big one, the speed of light, c.
299,792,458 meters per second. Unforgettable.
Well, it's not just about how fast light travels, right? It's the universal speed limit. Nothing goes faster. Not objects, not energy, not even information.
It sets the rules for causality, basically, which events can affect other events.
Exactly. And famously, of course, it links mass and energy through EMC phi, that little equation.
Can't escape that one.
So the fact that c is involved means the Planck scale has relativity baked right into it. The finite speed of information, the way space and time are linked, it's all crucial.
Okay, constant number one, c. What's next?
Next up, the force that, pulls us all together, quite literally.
Gravity. The gravitational constant, g.
That's the one, approx 6.674 I 10 inverse. Tiny number, usually.
Yeah, we use it in Newton's law, but you're thinking bigger picture, right? Einstein.
Exactly. In general relativity, g tells us how much mass and energy actually warp the fabric of space-time. It quantifies that curvature.
And bringing g into the Planck scale discussion means what? Gravity suddenly matters down there.
It matters hugely. Usually gravity is super weak on tiny scales compared to, say, electromagnetism, but down at the Planck scale, it becomes just as strong as the quantum effects.
So space-time isn't just a passive stage anymore.
Not at all. It becomes an active player. Its own quantum nature starts to dominate. You can't ignore it.
Okay, C and G. Relativistic gravity. What's the third pillar?
The third one brings in the quantum weirdness, Planck's constant, usually written as H or often the reduced version, a Taido, H bar.
The heart of quantum mechanics.
Absolutely. It tells us energy isn't smooth and continuous. It comes in discrete packets, little lumps called quanta. That's the Planck-Einstein relation, E equals h nu, or hc over lambda.
Energy quantization. Got it.
And crucially, Haas is also the key player in the Heisenberg uncertainty principle.
Right, the one that says you can't perfectly know certain pairs of things at the same time, like position and momentum.
Precisely. It sets fundamental limits on measurement itself, so the mere presence of S confirms the Planck scale is inherently deeply quantum. Uncertainty, probability, quantization. It's all down there.
A granular universe.
Yeah, at its very heart, yeah.
So, okay, CG and S, the speed limit, gravity strength, and the quantum greeniness. These aren't just random numbers then.
Not at all. They're like universal conversion factors. They set the relationships between mass, length, time, energy, basically allowing the universe to define its own natural scale, completely independent of us humans and our meters or kilograms.
Which leads us to Max Planck himself.
Back in 1899, yeah.
Here's where it gets really interesting. He had this, well, frankly, astonishing insight. Combine these constants.
Right, just play with them mathematically using their units, what we call dimensional analysis.
Yeah, and what happens?
All the human units, meters, kilograms, seconds, they just cancel out. Poof, gone.
Leaving
Units defined purely by the universe itself, by G, C, and G. He found a natural unit of length.
The Planck length. 8 used by E20 by 820 by 99.
That's it. The formula is the square root of AG over C cubed, and it comes out incredibly ridiculously small, about 1.6 times 10 to the minus 35 meters.
1.6 by 10 uniter? That's hard to even imagine. A millionth of a billionth of a billionth of a billionth of a meter, something like that?
Something like that. Utterly tiny, but the key isn't just the number, it's how we get it. The universe itself provides the measuring stick.
Mind-blowing. But the Planck length is just the start, right? You mentioned a whole family.
That's right, the whole Planck family. You can combine the constants in different ways to get other natural units.
Like Planck time, TRW by 820 by 820 by 99.
Yep, that's just the Planck length divided by the speed of light, by 20 by 820 by 99c. Comes out to about 5.4 times 10 to the minus 44 seconds.
The shortest possible tick of a clock, conceptually.
Kind of, yeah. The time it takes light to cross one Planck length. Then there's Planck mass, men0 by E20 by 820 by 99.
Which is, and that one's weirdly not that small, comparatively.
Right. It's about 22 micrograms, 2.18 by neurograms. Tiny for us, sure, like a flea's egg.
But for a fundamental particle, like an electron, that's enormous.
Colossal, exactly. And that mass corresponds to the Planck energy, E0 by E20 by E20 by 820 by 99 CSU, about 1.22 times 10 to the 19 giga-electron volts.
Which is a staggering amount of energy for particle physics. Way beyond anything the LHC can reach.
Orders and orders of magnitude beyond. So these aren't just mathematical games. People started thinking they represent something physically real. John Wheeler, especially in the 50s.
Wheeler. He championed their physical significance.
He really did. He theorized the Planck scale isn't just a unit system, it's a true physical boundary. He came up with the idea of quantum foam.
Quantum foam. Sounds messy.
Exactly. His idea was that if you could zoom in to the Planck length, space-time itself would stop being smooth. It would break down into this chaotic, fluctuating, turbulent, well, foam.
Where our usual ideas of distance and direction and even time order just stop making sense.
Precisely. Before and after might blur. Causality could break down. It's where general relativity and quantum mechanics collide head-on in a really dramatic way. Wheeler turned these units into a prediction about the limits of known physics.
Okay, one quick clarification, though. You mentioned h. Does using the original h instead change the numbers much?
Ah, good point. It changes the precise numerical factors slightly, like factors of 2 here and there. But the order of magnitude, the basic scale of tenometers or tenoseconds, that stays the same.
So the core message is the same. This is the scale where quantum gravity effects become dominant.
Exactly. That's the crucial takeaway.
So, okay, we have this incredibly small scale. Why can't we just measure it if we build a powerful enough microscope? Does the act of observation itself get in the way?
That's precisely where the trouble starts. It boils down to how we see things, fundamentally.
Using light or some kind of probe particle.
Right. And the rule there comes from the Planck-Einstein relation again. Eq. To see smaller details, to resolve finer features.
You need a shorter wavelength, like using blue light instead of red light for a sharper image.
Exactly. But the equation tells you if you shorten the wavelength, the energy E must go up. Shorter wavelength means higher energy.
So to see something incredibly tiny, like near the Planck length,
you need an incredibly energetic probe photon. Simple as that.
But this isn't just about needing more power. It's where Heisenberg comes back in, right? The uncertainty principle.
Yes. The act of measurement itself starts to dominate. Heisenberg's famous thought experiment, the gamma-ray microscope, illustrates this perfectly.
Walk us through that again.
Okay. Imagine you want to pinpoint an electron's position very precisely. Small uncertainty in positions.
To do that, you need a light source with a very, very short wavelength, like a gamma ray.
Right. But a short wavelength gamma ray, according to Planck-Einstein, has incredibly high energy and therefore very high momentum.
Okay.
Now, to see the electron, that gamma ray photon has to bounce off it, scatter off it.
And when it does?
It gives the electron a huge kick. It transfers a significant chunk of momentum. And crucially, because of the way scattering works at this quantum level, you don't know exactly how much momentum was transferred. There's a large uncertainty in the momentum transfer.
Ah, so trying to nail down the position, small x, means you introduce a huge uncertainty in its momentum,
Yeah.
large deck.
Exactly. X times gap has to be greater than or equal to 2. There's a fundamental trade-off. Precise position measurement means you completely mess up the momentum. Precise momentum measurement means you lose track of the position.
And this isn't because our detectors are bad. It's baked into nature.
It's an intrinsic feature of quantum reality. Measurement isn't passive observation. It's an interaction that inevitably disturbs the system.
Okay, so quantum mechanics tells us our probe needs huge energy and inherently disturbs things.
Yeah.
What does general relativity add to this picture?
General relativity tells us about the consequences of packing all that energy into the probe. Remember, gravity doesn't just come from mass.
It comes from any concentration of energy and momentum. EMCAC works both ways.
Right. Even a photon, which has zero rest mass, carries energy and momentum, so it creates its own gravitational field. It warps space-time around it.
Usually that effect is absolutely tiny, negligible for a single photon.
Completely negligible in everyday life or even in most physics experiments. But if you need a photon with Planck energy to probe the Planck length,
then its gravity is not negligible.
not at all. It becomes overwhelming. This leads us straight to the concept of the Schwarzschild radius.
The point of no return for a black hole, RS, 2GM/cm.
Yep. It's the radius where space-time curvature becomes so extreme that nothing, not even light, can escape.
And crucially, the m in that formula can just be energy divided by c squared.
Precisely. Any concentration of energy, if packed densely enough, will reach its Schwarzschild radius and collapse into a black hole.
Even pure energy, like light.
Theoretically, yes. That's the idea behind a Kugelblitz. A black hole made purely from light or radiation.
A ball lightning black hole. Sounds exotic.
It is. But here's a fascinating twist from recent research. It looks like forming a classical Kugelblitz might actually be forbidden.
Forbidden by what?
By quantum effects, specifically the Schwinger effect.
The Schwinger effect. That's where strong fields create particles out of nothing.
Sort of, yeah. In extremely strong electromagnetic fields like the ones you'd need to try and concentrate enough light to form a Kugelblitz, the vacuum itself becomes unstable.
The vacuum. Empty space.
It's not truly empty in quantum field theory. It's fizzing with virtual particles. And a strong enough field can rip these virtual pairs apart, making them real particles, usually electron-positron pairs.
So trying to make the Kugelblitz
Causes the vacuum to basically boil, spitting out particles and radiation before you reach the black hole density. These new particles would carry energy away, preventing the energy from concentrating enough to actually form the classical event horizon.
Wow. So the wall isn't quite a sharp black hole edge, it might be this. Quantum fizzing that stops you first.
It suggests the barrier might be fuzzier, a more complex quantum gravitational boundary. The vacuum itself actively resists being probed that intensely. It doesn't necessarily mean the Planck limit is wrong, but the nature of the barrier might be different, more quantum than just a simple mini black hole. It's cutting-edge stuff.
Okay, this is getting intense. Let's try to bring it all together then. Our sources gave two main arguments for why the Planck length seems to be this ultimate operational limit. Argument one was the photon probe thought experiment.
Right, the detective story.
Let's walk through it step by step. One, you want to measure something the size of the Planck length, OD2 and by 820 by 820 by 99, about 10 meters.
Requirement. You need a probe with a wavelength less than or equal to 80 by 20 by 820 by 99. A ruler mark that finely.
Two, consequence. Planck-Einstein means this probe photon needs immense energy. If 80 by 820 by 820 by 99, the energy E is the Planck energy, 80 by 820 by 820 by 99, about 10 meters F. Huge, colossal energy.
Three, the collapse. General relativity kicks in. That much energy packed into a region roughly the size of the Planck length. Well, it has a powerful gravitational field. Calculate its Schwarzschild radius.
It says 2GE0 by E20 by E20 by 99 CO, essentially. You plug in the Planck energy.
And you find the Schwarzschild radius is also on the order of the Planck length. Maybe twice the Planck length, depending on the factors of 2.
Right around 8020 by 820 by 820 by 99.
And that brings us to step 4, the paradox. The very act of creating a probe photon energetic enough, short enough wavelength to see the Planck length
Creates a gravitational field so strong it forms a micro-black hole, or this opaque quantum state we just discussed.
whose event horizon, or fuzzy boundary, is bigger than the Planck length you were trying to measure in the first place. It swallows the information. The probe itself obscures the target.
Just like trying to measure the width of a hair with a wrecking ball. The tool destroys the measurement.
Exactly. And if you try to get even better resolution, say, over O's on get E20 by 82 member 99210.
You need even more energy.
Which makes an even bigger black hole, obscuring even more. It's a catch-22.
So the Planck length emerges as the smallest distance we can meaningfully talk about measuring, because the process of measurement itself breaks down right there.
It becomes operationally undefined. That's the key.
Okay, that's one powerful argument. What was the second one? The crossover?
Ah, yes, argument 2. The crossover of fundamental scales. This one feels even more fundamental, maybe. It's not about a specific experiment failing, but about an intrinsic property of physics itself.
How does that work?
It involves comparing two different length scales associated with any particle, scales that depend on the particle's mass in opposite ways.
Okay, what are they?
First, there's the Compton wavelength. accuracy equals HMC. This comes purely from quantum mechanics and relativity. It sort of represents the scale at which a particle's quantum wave nature becomes really apparent. It's the scale below which you can't really localize the particle without having enough energy to potentially create new particles, like particle-antiparticle pairs, out of the vacuum.
So it's like a quantum fuzziness scale. And how does it depend on mass?
It's inversely proportional to mass, pre-HMC. So the more massive a particle is, the smaller its Compton wavelength. It's easier to pin down heavy particles.
Okay, AUC gets smaller as mass increases. What's the other scale?
The other one is the Schwarzschild radius, RS equals 2gmc flourish from general relativity. The black hole radius.
Right. And that one, whereas this is proportional to mass, the more massive something is, the larger its Schwarzschild radius.
Exactly. So you have these two fundamental scales. Compton wavelength getting smaller with increasing mass, and Schwarzschild radius getting larger with increasing mass.
They're going in opposite directions. They have to cross somewhere.
Precisely. There must be a unique mass where these two scales become roughly equal, where ACRs.
So what happens if you set HMCA to 2GMCA and solve for that mass?
You rearrange it. And the mass you find is, remarkably, the Planck mass. M is 0 by E20 by E20 by 99 equals 820 by 99, ignoring factors of 2 and pi for simplicity here.
Wow. So the mass where a particle's quantum fuzziness scale equals its black hole scale is the Planck mass.
Yes. And if you then plug that Planck mass back into the formulas for either the Compton wavelength or the Schwarzschild radius.
Let me guess. You get the Planck length.
You get something on the order of the Planck length. O by 820 by 820 by 99 equals for both.
So the Planck scale is this unique fundamental point built into the laws of physics where
a particle's quantum wave nature, its inherent uncertainty, and its gravitational nature, its tendency to curve spacetime into a black hole, become equally important and operate at the very same length scale.
it's like the point where a fundamental particle, just due to its own quantum fuzziness, effectively is its own black hole.
That's a great way to put it. It shows the Planck scale isn't just about our measurement limits. It's deeply woven into the consistency of quantum mechanics and general relativity themselves.
Okay, so this limit isn't just a weird paradox. It's almost a signpost, pointing towards where our current theories need to merge. A clue for quantum gravity theories.
Absolutely. It's a crucial guiding principle. Any theory trying to unify gravity and quantum mechanics has to grapple with the Planck scale and what happens there.
So how do the leading contenders, like string theory and loop quantum gravity, incorporate this?
They approach it in different ways, but both inherently include a minimum length scale related to Planck length. Let's take string theory.
Okay, strings instead of point particles.
Right. The fundamental objects are tiny, vibrating, one-dimensional filaments of energy strings. And these strings aren't infinitely thin points. They have a characteristic size, the string length.
Which is assumed to be.
Generally believed to be somewhere around the Planck length, maybe slightly larger. So right there, the theory has a built-in physical minimum size. You can't probe smaller than the string itself.
Building blocks have a size?
Exactly. Plus, string theory has this weird property called T-duality. If you imagine extra dimensions curled up really small, T-duality suggests that trying to probe distances smaller than the string scale in that dimension is actually equivalent to probing larger distances. It sort of bounces back, reinforcing the idea of a minimum length.
Okay, fascinating. What about the other big approach? Loop quantum gravity, LQG.
LQG takes a very different path. It doesn't assume strings. Instead, it tries to directly quantize space-time itself, applying quantum rules to Einstein's geometry.
So space isn't smooth and continuous in LQG.
No. It predicts that space at the Planck scale is fundamentally discrete. It's made up of a network, like a shimmering web, of quantum relationships, these things called spin networks.
Like atoms of space.
Sort of. The theory predicts that there are minimum possible non-zero quanta of area and volume. You can't have an area smaller than a certain value or a volume smaller than a certain value.
And these minimum areas and volumes are determined by?
They're determined by the Planck length. So in LQG, the Planck length is effectively the fundamental pixel size of space itself. Space-time has an atomic, granular structure at its core.
Wow. So both leading theories, in very different ways, end up suggesting that space isn't infinitely divisible, that there's a fundamental limit around the Planck scale.
That's a major convergence, yes. The details differ wildly, but the existence of a minimum length scale seems to be a common theme.
Okay, let's try to synthesize this. Circling back to the original question about a minimum frequency length or minimum wavelength, is the Planck length definitively that limit.
Effectively, yes. As we saw with the photon probe argument, if you try to create a photon with a wavelength as short as the Planck length,
It needs Planck energy.
and that Planck energy, confined to that tiny Planck length volume, inevitably collapses the region gravitationally. It forms a micro black hole or that fuzzy quantum boundary state,
Making observation impossible. The probe fundamentally alters, or rather obscures, the target.
The measurement prevents itself. So operationally, 1 Argray 20 by 820 by 99 acts as the minimum resolvable wavelength or distance.
We should probably re-emphasize a couple of nuances here, though.
Definitely.
First, the exact number, 1.616 times 10 eurometers. That specific value depends slightly on whether you use H or H in the formula, right? A human convention.
Correct. There might be factors of 2 or Prol floating around depending on precise definitions, but the order of magnitude, the 10 to the minus 35 part, that's the physically significant thing that pops out naturally from G, C, and X.
That scale is robust.
Very robust. Second nuance, remember the Kugelblitz and Schwinger effect discussion. The actual barrier might not be a sharp classical black hole event horizon.
It could be a more complex quantum gravitational phenomenon, vacuum breakdown, particle creation.
Exactly. It might be a fuzzier wall, but still an impenetrable one for our probes. This is where active research is happening, understanding the true nature of that barrier.
And the biggest caveat of all, these are still extrapolations based on combining quantum mechanics and general relativity, where we expect them to break down or merge.
Right. We don't have the final, complete, experimentally tested theory of quantum gravity yet. That's the ultimate goal, to get the definitive picture.
So pulling it all together, what's the big takeaway message for us, for you listening?
I think the big picture is that the Planck scale seems to represent this really profound emergent boundary in nature. It's the scale where our methods of observation, our probes,
Become tangled up with the very thing we're trying to observe, the geometry of spacetime itself.
Exactly. It's the point where asking a question about the structure of space, using the tools physics gives us, physically prevents an answer from being returned. Not because our tech isn't good enough, but because the laws themselves seem to impose this limit.
So it's not really a failure of our current theories, GR and QM.
In a way, it's a prediction from their logical consistency when pushed to their combined limit.
The Planck scale reveals this humbling ultimate boundary that physics, as we understand it now, places on our ability to know the universe at its finest grain.
It really is the point where the map of our physical theories and the territory reality itself seem to kind of dissolve into each other, where asking becomes impossible.
And maybe exploring that boundary is the most fascinating journey of all.